Today we are going to see an interesting paper on entity matching task. So the entity matching in this case is evaluated against the state-of-the-art transformer architectures. And okay, let's first see the abstract of the paper and we'll get going ahead. So in this paper, if you see, the the task of entity matching is primarily evaluated against the four state-of-the-art transformer models, that is the BERT, XLNet, Robert, and the DistilNet. And the task is essentially done on textual data and dirty data. Dirty data refers to the data where the entity types and the entity values are not mapped one-to-one. It is kind of scattered across the different entity types. So the task of entity matching is even more difficult. And all the comparisons done are empirically compared against the difficult data sets so that we can get a view of how each of these architectures perform. Okay, now maybe we will introduce the EM jargon a little bit. So entity matching is the task of determining whether the two real world objects are the same as what is described in the text. So for example, in this product description, if you see, there are two descriptions for the mobile phone. The first one talks about Apple's iPhone XS and the related configuration, and the second one talks about a smart device with a decent price, Nokia's PureView, and so on and so forth, right? So there are two descriptions for the mobile phones. Now it's up to us whether to conclude whether these two are talking about the same phone, or are they talking about the phone as a real world object or something else. So as a human, based on the question asked, it is still quite easy to kind of answer this question, but from an algorithm point of view it becomes fairly tricky and non-trivial fairly quickly. So that is what we are trying to see, how we can solve such problems using entity matching. And one of the other key aspects of entity matching is that in the data integration and data cleaning space, now most of the systems in the world are big data systems, and we can very well visualize that the flow of data per minute in any online system, or any system for that matter, is pretty huge. So there's a deluge of data coming in, and there's a constant need to kind of integrate the data and clean the data in such a way that the duplicates are removed on a consistent basis, right? So it's a very core task in any data environment today. Now, so there are various works done. We will be seeing the relevant works done in the past, and how the transformer models fare as compared to those works. But one of the key works done in the past is the Magellan project, and this project is essentially a conventional project. It's not based on any deep learning techniques, but it's a conventional project and has been one of the pioneer projects for quite a long time, and still it is performing very well on structured data. So when we say structured data, is something where the entity types are clearly defined, entity types and the entity values are mapped with each other in a very neat way, and there is no crisscross across the entity types and entity values. So this is something, if the data is available in such a format, then Magellan Project performs very well. But the problem is, to get the data to such a state is a very big challenge, because the data labeling effort in case of text is pretty huge. So that's the key reason we are going towards something which can handle all the dirty stuff in the data itself. Okay, and there are few other papers mentioned in these references. You can check it out, which are based on the deep learning stuff, and this is more towards the textual data or the dirty data. So we will be comparing the results across these techniques as well when we talk about the transformer results. Okay, now let's talk about the key contributions of the paper which we are talking about. Here the paper first tries to compare the four transformer models which are kind of the state of the art as of today: BERT, XLNet, DistilBERT, and Robert. Okay, and after that the experiments also demonstrate how the how the transformer techniques compare against the classical deep learning techniques in EM. One of the key techniques is the deep matcher, which is one of the state of the art in the deep learning space, and we will see how the transformers kind of beat the deep matcher by more than 27.5% gap of F1 score, and that's a pretty huge gap. And also, when we talk about the transformers, one key aspect is the training, and we will see how much of training is required, and what kind of hardware setup is required to do the training, and all that heavy stuff which is required to get the required result. And we will see that it doesn't take too much of fine tuning. I mean, the pre-training of course will take a lot of time, but the fine tuning of the transformer models is not that much as compared to I mean to get the required result. So we will see that as well. Okay, yeah, I think we discussed about the Magellan, and we already discussed that it is pretty good in the structured data records, right? And yeah, and but it is a conventional system, so that's the need of going towards the deep learning stuff, and it essentially, as we know, removes the need for any handcrafted features totally, and it generates the required features internally, or at least in the latent form. Okay, so now with respect to transformers, definitely the results are pretty good, but there is also a consistent talk about the heaviness due to which a lot of projects fail to use transformers in the real world production settings. So that's why we have I am specifically going through the models and the computational time mentioned in the paper. So the authors of the paper have very clearly put a lot of effort on the power consumption and also the training time requirement of these models. So that's a very good positive aspect mentioned in the paper by the authors. And a bit about Rnns, because when we talk about transformers, we have to know why we are not using the Rnns. And one of the key aspects of the Rnn is that it tries to capture all the latent embeddings within one vector, and that causes this bottleneck problem. Essentially, specifically when the sentence is quite long, we tend to lose the aspects of the sentence which are aspects of the words which are occurring fairly in the beginning of the sentence, right? So that is something which is not desirable, and this causes the bottleneck problem, due to which we usually move towards LSTM or GRU. That is one aspect. Second thing is that the Rnn is not parallelizable. It's more of a sequential model, same with LSTM and GRUs as well. And even though the long range dependencies aspects are hard to learn with Rnn, and we go towards LSTM and GRU, but still the parallelizable issue remains the same in this case also. There are several tricks applied in today, but still it's not giving, it doesn't give the result as expected. That's where the attention comes into picture. It resolves the bottleneck problem. It is parallelizable. It can attend to any part of the sentence without worrying about the distance, and it also can attend multiple words at the same time. So that is a key reason why we have moved towards attention. Essentially, attention talks about the principle that a word can be represented as a weighted combination of its neighborhood, right? I'm not going into too much detail of attention, but the authors here have they are giving some intro about each of the techniques, so that we are aware that what we are discussing about. Okay, and yeah, so this is a demonstration of the self-attention. So if you see this sentence here, the animal did not cross the street because it was too tired, right? So the animal here actually is actually referred with the word it here, right? And it's pretty long. I mean, there are around 3, 4, 5, 6, 7, 8 words in between, and RNN may not be able to attend to it in an efficient way. And even for LSTMs, we have to kind of skip all these sentences in between. So that's where the self-attention comes into picture, and it very neatly if you see this highlight kind of a heat map, right? So the animal is very neatly I mean, it talks about the it word here, and that is pretty much it what we want. And so that is the key reason why we are going towards self attention. And we can of course put this kind of a block. There can be multiple blocks here, and there can be multi-headed attentions, right? And that will help to kind of attend to many words, not only the single one-to-one mapping as we have seen here. Okay, and as we know, the transformers have the encoder decoder architecture, and the decoder has access to all the states of the encoder, right? So that's how we kind of map between the input and the output during the training, and the decoder essentially is used in the inference time. Okay, and now moving towards a bit about transformers. So yeah, the transformer uses self-attention, as we have seen above. It replaces the Rnns completely, so it's a major transformation in the architecture. And in addition to the self-attention, it also uses a multi-headed attention, as I just showed above. That instead of just attending to one word, we can make the architecture attend to many words within itself by putting more number of attention blocks. That is about the multi-headed attention. And during training, the dependencies are learned independently on both the source and the targets, right? So that is something which is important. And yeah, so this is a sequence. This is a general sequence to sequence model. So if you see, this is the encoder model here, and this is the decoder model. And sorry about this. This is the encoder model, and this is the decoder model. And if you see, this is the weighted combination of the words. So each word here is a weighted combination of the words here. And if you see, one input is coming from the encoder, and the other input is coming from the decoder, and it is a linear combination of the weights, and the weights can be learned through a neural network. So essentially, and basically each word here, we will know which words are contributing more from the encoder architecture and also from the decoder architecture, right? So that is something which is very intuitive in case of attention. And yeah, and in case of multi-headed attention, essentially in the decoder, we also have one more multi-headed attention which attends to the encoder part, typically like this, what we have shown here, encoder and the decoder, right? So we have one more multi-headed attention to replay to kind of mimic this. So that is about the attention mechanism in transformers. Second important mechanism is positional encoding. This is essentially because, as we have seen till now, we are essentially talking about the linear combination or a weighted combination of the words from the encoder and decoder to get the final word or the prediction here. And this is something not considering the order of the words into account, right? And that is where the positional encoding comes into the picture. It's a very novel idea. We will not go into the detail, but we can check out this reference. So there are a lot of nuances mentioned here in order to capture the order of the words. And third important aspect is the residual connection, in order to do away with any kind of gradient, dying gradients, or shooting up the gradient problem, vanishing gradient or exploding gradients essentially. And this is something which is not novel to this transformers. It is very well described in various architectures, and it was first introduced in the ResNet architecture of the CNN block. Okay, so we have got a quick summary of what transformer constitutes of, and now let's talk about BERT. BERT is a natural extension of the transformers, and here we are basically essentially talking about BERT, XLNet, raw BERT, and distal net. And if you talk about only about BERT, BERT is nothing but a bidirectional encoder representation from transformers. It's bidirectional, so that is a key word here. We will talk about why it is important and how does it make an impact. And this is a standard transformer architecture. I think we have gone through it many times, and I will not be going through this. But one thing I want to highlight is the multi-headed attention part, which is mentioned here, which kind of links with the encoder as well, right? So this helps us to get the attend to the important words in the encoder vis-a-vis the decoder. Okay. One aspect of BERT, now coming back to BERT, one aspect of BERT, what the authors have mentioned here is the it is jointly conditioned on the left and the right context of the query during pre-training. So this part we know anyways from the BERT paper, but this is something very important here. And if you see the left to right dependency is mentioned something like this. So the word into depends kind of on the words which are occurring before that, that is the problems and the turning, not essentially not essentially depending on the words which are mentioned here, right? And this is something which is fixed in BERT. So if you see the word here depends on the words which are occurring before and the words which are occurring after as well. So it's a kind of a bidirectional in that setup, and this is one of the crucial ideas discussed in the in the BERT paper. Okay, instead of predicting the next word, so we kind of predict the masked token. So that is essentially, so it's similar to the word to wake concept as well, where we kind of try to predict the focus word given the context words, right? It's kind of related to that. So this is one task on which the BERT is pre-trained. So we have to understand one thing, that the BERT model or the set of the related models as well, basically BERT and the other models are essentially are trained on two tasks in an unsupervised way and on the unspecific data. When we say unspecific data, it can be generic data, but a very large corpus of data, and it is trained on an unsupervised way. So as we said, this is something like a word to vec model, right? And word to vec also, if we know, it's an unsupervised technique to get the word embeddings. So this is a first unsupervised task which and pre-trained on large number of a large corpus of data. And the second unsupervised training, what is done is a next sentence prediction. And this is pretty intuitive, because if you take any question answering a database or a natural language inference or entity matching, so we will get a lot of data, and so that is something which is used to train the NSP task as well. So there are two tasks which are trained in the unsupervised way using large corpus of data, and it is pre-trained. So whatever model we take will be pre-trained on these two tasks. This is very important to know, because the final task what we are going to perform using the BERT model should be relatable to these two tasks. Otherwise we may not get the desired result. If so there are only two options in that case: either we find a suitable pre-trained model, else we spend the compute and the required compute power and then pre-train the model on the specific task, and then we use it to fine-tune. So that is those are the two approaches. Okay, now let's talk about a bit about the ablation study done on the BERT. And if we see the most important aspect of the ablation study is the bidirectional component here. So the left and right context is the most important feature which is adding to the accuracy and the performance of BERT. Right, and so that's about BERT. Now let's talk about XLNet and Transformer XL. So XLNet model talks about the shortcomings and how they fix that, shortcomings of BERT and how they fix that. The two major downsides: one is the predicting the mask, as we saw above in the bidirectional setting. It is done so essentially these masks are artificial symbols here, right? And so that is something which never occurs in the downstream tasks. It is a kind of a artificial symbol. So they try to fix it in order to improve the performance. And second is that these masks are not tokenizable. These are not parallelizable, and they are dependent on each other. And there is a huge shortcoming which they have identified because of this, and they have tried to fix this as well through something called auto regression. Okay, we will see that. And so this example is the independence assumption which we just saw above. So if you see that there are two masks tokens here, there are three mask tokens here, and if we and there is no relationship between these two. That is the key thing what they are trying to mention through independence assumption. So this set of tokens and this set of tokens are kind of independent, even though in these two cases it is correct. But if we see in this case, it is not correct, because these two are not dependent on each other. That is a problem, and they try to actually fix it. So that is a thing which we will see. And that is done through a technique called permutation language modeling. So permutation language language modeling is nothing but if you see this figure here in the right side, so So this is the actual sentence. New York is a city, right? And the factorization order is mentioned as 1 2 3 4 5. So each word token has been given a number here. And in the first permutation, if you see, the sequence is jumbled up, 4 2 1 3 5. And in the second, again is jumbled up. So right, so this that logic behind the jumble is given here, permutation 1 2 and 3. So essentially what they are doing is they are kind of jumbling up the words and still trying to predict the masked token. So in a way that kind of captures the dependency, or it kind of tries to come out of the independence assumption. It kind of captures the independencies. So that is the way they have fixed it. But yeah, so that is about the permutation language modeling. So essentially, if you just see this, it is mentioned very neatly here. The ability to learn the dependencies beyond a fixed length without disrupting temporal coherence. This is possible due to the segment level recurrence mechanism and a novel positional encoding scheme, right? Yeah, so this is the other contribution of BERT, the kind of the independent assumption, essentially what we talked about. Okay, so the key thing to note here is that no mask tokens, no artificial characters, and second thing is coming out of the independence assumption. Now let's come to the Robert paper. Now Robert paper is a very interesting paper. It talks about that they are not doing anything new. Rather, they argue that the authors actually claim that without doing any major changes in the architecture, essentially, and fine tuning other aspects of the of the architecture, like training data and so on and so forth, we will see that they are saying BERT itself is sufficient to give state-of-the-art results, right? And we have to just fine-tune in the hyperparameters and give enough data. So first thing what they did was they gave more data. Instead of 16 GB of data, they gave much more data. So they gave around 160 GB of English text, longer training times. So essentially they tried with training durations with 10,000 steps, 3,000 steps, 5,000 steps, and then they show that longer duration gives better results. Larger batch size. So essentially they see that instead of giving 256 as the batch size number, they tried with 2,000, 8,000, etc. And they finally found that 2,000 is the best mini batch size to get the required result. And they got rid of this task of next sentence prediction, and also so that is one thing. And they also try to give the full attention span instead of a subset. Basically they are giving a full attention to all the 512 tokens of the BERT. And lastly, they also try to change the masking pattern of the training data dynamically, unlike the static way in case of BERT, right? And doing all this, it achieves state-of-the-art results. So without changing anything in the architecture, by tweaking the other aspects of the architecture design, they are able to get the state-of-the-art results. So that is about the Robert paper. And DistilBERT is quite opposite. It's a very lightweight model. The intention of DistilBERT is to use as smaller model as possible without, of course, trading off the accuracy to a large extent. And if you see the comparison here, BERT has around 340 million parameters, Robert has 355 million parameters, and the much larger training size. And there was another model from NVIDIA which used around 8300 million parameters, right? So there is a clear need of a lighter model. And there are various ways in which the model can be compressed. There are techniques like quantization, weight pruning, distillation, and DistilBERT authors tried to use the technique of knowledge distillation. In summary, the technique of knowledge distillation is to have a teacher-student kind of a learning paradigm, where the teacher model will have the major of the pre-training done, and the student model will be a kind of task specific, right? Yeah. And okay, now one more aspect is that they have kind of purge the token type embeddings and the pooler, and this kind of reduce the model size by 40%. So that is another aspect of the student teacher model. And doing all this, DistilBERT retains 97% of the BERT model while reducing the size by 40% and being 60% faster. So net this kind of summarizes that DistilBERT was able to achieve what it was supposed to do. Now, since we have seen all the 4 architectures, now let us see how they perform as compared to the conventional solution of Magellan, and also the other state-of-the-art deep learning techniques like deep ER and deep matcher. Okay, essentially we are trying to get answer to the following questions. Essentially we are trying to see how well do the transformer architectures perform compared to the traditional techniques, as I just mentioned, and then how they are compared to the state-of-the-art deep learning techniques, which transformer is the best out of all these 4 which we have seen, and how much training time does it take to fine tune them, right? So these are the things which we will see. And the data set, now coming to the data set part. So data set, there are various types of data set available, like structured data set, then textual data set, dirty data set. So Magellan, as we discussed, is very good in the structured data set, and deep matching. So that's one of the reason why deep matching algorithm and the deep ER algorithm didn't put too much effort on the structured dataset part. Rather, they put a lot of effort in the textual and the dirty datasets, right? Textual and the dirty datasets. So that's why we will also focus. Rather, the authors have focused more on the 5 dirty and the textual datasets. So these are the datasets mentioned here, right? And yeah, next let's talk about the hardware setup required to do the fine tuning. So remember, we are not the authors have not done any pre-training here. They have just done the fine tuning here, assuming the task is already pre-trained with. So it's a pretty standard hardware setup. So they have a single NVIDIA Titan XP GPU with 12 GB memory, which is pretty decent, not too big. Then Intel Xeon 4 core processor and 8 GB of RAM. It's a pretty simple setup. And then yeah, with respect to the method, maybe I will go to the architecture, or rather the block diagram shown here is pretty neat. Okay, so let's just understand how the data is pre-processed before it is pushed into the BERT models, BERT and the related BERT model. So first is a classification token, because we are ultimately doing the entity matching. So entity A and entity B, right, are tokenized, token A1 token till token AN, and similarly from B1 to BM. So there are N tokens in entity 1 and there are M tokens in sorry about this, there are M tokens in entity B and there are N tokens in entity A. And if you see, there is a separator here to make sure that both these tokens are separated out. So we have these 2 flags, and then yeah, then it is basically so this is one part of the setup. The second is the positional and the segment embeddings. Positional embeddings are shown in this layer, so AE, A1 to AN, and segment embeddings are shown in this layer, right? Sorry. So once all these are concatenated, then we have the required input setup to pass on to the model, right? And yeah, we are not going inside the details of positional and the segment embeddings. This is something more discussed in the transformer papers. Maybe you can check it out in the reference section. Okay, and yeah, so with the above setup, what we have done, we are evaluating all the 4 transformer architectures as mentioned above, and this is an interesting insight into the architecture. So as we can see, BERT is around 12 layers, 768 hidden words and 110 million, and XLNet also is similar, and is also having similar number of parameters. Robot is a little bit heavier model, and DistilBERT is much lighter, right? But the key thing is that all are using the 768 embedding. So the embeddings what we had discussed here are 6 is of the size of 768, and then there are 12 heads, multi-headed attention models. Okay. Okay. Lastly, we'll just discuss about this, and then we will talk about the comparison of the results. So here we are talking about the pre-trained model. So the prerequisite for all this training is a pre-trained model. The authors have also tried to give a brief about the kind of compute required to train the models. We know that it's pretty heavy in terms of both the dataset size and the compute uh, computing power requirement, but the essentially the numbers are something like this. For the BERT large model, there are 64 TPU chips required for 4 days. So this much of training is required in case of BERT large, which is pretty huge, I would say. Then in case of Robert, 1024 Volta 100 GPUs. Volta 100 GPUs are one of the most powerful GPUs out there, right? And we need 1024 of that, and the training time will be approximately 1 day. So it's a huge computation effort with respect to the pre-training task, and that is one of the reasons these models are so popular, because this is already done by the original contributors. So we just have to maybe fine-tune the model. That's the thing. We'll talk about the fine-tuning effort shortly, but before that, let's see the results as compared to the Magellan and the deep matcher. This is the best transformer model output, and this is the delta in the F1 score. So as we can see, the authors are claiming that the best transformer models are giving pretty decent accuracies, and wherever the scope is more to get the higher accuracy, there we can see a big delta, and wherever the scope is less, still we have some delta, but it is not significant, right? But nonetheless, it is a pretty decent, or rather a very good outcome from the transformers. Okay, so let's see this in the case of using some charts. So if you can see, one key aspect what I want to mention here is that so this is for the dataset, first dataset, and if this is as a plot across the F1 score and the number of epochs, and if you see right after few epochs, say around 3 epochs itself, we are able to get a very high F1 score. This is in case of the Robert model, and it kind of maintains this momentum till the end. And by the count of say epoch 5, we are able to come into the zone beyond which we don't get much more improvements. And same is true in this case as well. One of the reasons why there is a sudden dip in the F1 score is because this is a very small data set, like around 130 odd records. But once the things start picking up, say around 3 and 4 epochs, after 3 and 4 epochs, again we are seeing a consistent results, right? Again, Robert performs pretty well in this case, in this data set also. And same trend we can see in this also. Again, Robert is performing pretty well, and for that matter BERT also, right? And if you see here also, BERT performs well. In this case, XLNet is coming second. Okay, and yeah, so let's talk about the main findings. So the main findings of this whole exercise claimed by the authors is that all the transformer models perform very well on the task of entity matching, as we have seen above, and based on the delta what we got in the table in terms of the F1 score. And even after a single epoch, they are able to come within the 5% interval of their peak performance. I think we also discussed about that in the above charts. And Robert gives the best performance, understandably so, because it's the heaviest model and with a large pre-training corpus, and we saw that in the table as well, and similar results can be seen with this dataset as well. We can see the Robert model is the best, and within 3 to 5 epochs we are able to come into the zone of peak performance. Okay, now let's talk about the interesting aspect of fine-tuning effort, right? So if you can see now, one thing I just want to mention once again is that as we discussed before, the transformers essentially are pre-trained on the unsupervised and unspecific task, huge corpus of data in an unsupervised fashion, and that effort we have already seen in the section of 5.2.4. This effort is specifically the second part of training, that is the fine-tuning effort. It's a supervised fine-tuning. The data should be labeled in this case, and it is a task-specific fine-tuning, right? And if you see the result, the training time requirement for this fine-tuning is pretty decent. I mean, it is somewhere from say 5 or 6 minutes for this data set, and as low as to around 7 seconds for this. So within 5 to 6 minutes, we are able to get the required outcome across these four models and these 5 data sets, right? And so this is something, a very good finding, I would say, from the authors, and I would really appreciate them for getting this kind of an insight. Yeah, I think whatever we have discussed is mentioned here. And finally, the two important conclusions, compared to the conventional techniques of say Magellan, the training time specifically, I mean the performance we have already seen in terms of the delta of the F1 score, it is pretty huge, around 25-30% of a jump we are getting in the F1 score. Now when we're talking about the training time, non-deep learning models like Magellan are kind of very fast in fine-tuning effort. Very less time is required, and that is understandably so. But if we compare the same with deep matcher or DPR, where the training time is around from 10 minutes to even 11 hours. So here the fine-tuning effort is very, very less as compared to that. This is primarily because of the unsupervised pre-training done with a large corpus of data. So that is the final result. That's the end of the paper as well. And the authors have given a lot of references here to go through, and these are pretty useful for that matter. But one thing I personally, even though the paper has been giving excellent insights about the transformers and the results, but one key aspect which I personally found missing is inference time, right? So we have seen the training time, and we have seen the performance as well, but what about the inference time and the space and the time complexity requirement during the inference? So that is something which I would like to have seen, but anyway, that's for some other day. Hope you liked the session, and please don't forget to give your comments and the feedback. I would definitely like to hear from you all. Yeah, thanks a lot, and have a good day ahead.